patching shaders. And so I'll do a little quick introduction of how and why we did it, how it looks. And then I'll show you two fundamental data types that are part of this library. You will see them all over when we do the patch demos. And then we do an actual demo where I'll show you the entry points to this world where you can patch the shaders. Then Kyle will have the fun part. He will show you how you can compose shaders with different functions and things like that. And in the end, we'll have a little bit of an advanced topic that is quite interesting for everyone who knows what delegates are, or who has written a shader before, who knows what is a shader method and things like that. And the last part, this is also the part, I think, that sets this prototype that we are showing, sets it apart from other visual shader editors that do not have this kind of dimension that we are going to show. And yeah, so let's start. Let's have a look at a very basic data flow graph of shaders. Can you see more? Yeah. So shaders are basically a data flow from the CPU through some functions, the shader code, to output, which most of the time is the text on the screen, so it shows something. And so this is a very straight data flow. There's no big, no crazy definitions that happen. It's basically a very straight data flow. So this is super well suited for visual programming. And there are actually currently two game engines that have very powerful shader editors. One of them is Godot, which is an open source engine. They have a very nice editor. And what you can do in their editor is basically you create this root node, and then for each, your root node represents a material. So it represents basically there's a whole shader pipeline that you can put on objects, models, and things like that. And then you have different inputs here on this side where you can plug in values that you generate with this visual code. And this is the same thing from Unity. I don't know who was first in research, to be honest. But it's very similar. You also have this root node that defines a material that is basically the shader pipeline. And then you can plug into each of the properties of this material, you can plug in this graph, and then this graph generates some shader code. It then gets evaluated, compiled and evaluated by the GPU. So now the interesting thing was that if you look into the Xenko manual, you can read there, use a custom shader. This is under the section materials. There, for example, if you want to have a diffuse map, you have options here, you can use the vertex color, you can do your fixed color, or you have this shader option. And if you choose this shader, you can write a shader and put this shader there. And then you have basically the same thing. You just don't have this visual editor. And I talked with Vigil about this a little bit, and he told me that there was actually a plan in Xenko to do something like this also for Xenko. And they basically kind of already started to implement a system that is capable of doing that. And they called it compute color. And or basically this was the start they did. So compute color is basically something that represents a color that you can plug everywhere. And behind this compute color value, could be some shader code that you write. So in the end, this Y here is a color, and you can plug it anywhere in the material pipeline. And then you write shaders that compute colors. So we had a look at it, and we thought, okay, cool, that's very nice. You can define colors. Why not do every vector type or matrices? So basically all types you have in shaders, which are from floats to for everything. So we have something now in the patch, you will see that very soon, that is called var of t. And this t stands for or represents any type that is valid on the GPU. And so now what we have here, if you see this var type, you can, like, this represents a value on the GPU. And it's basically, behind it is some shader code that computes a value y. And then you can use this value y, plug it somewhere in the shader pipeline. We'll see that in a minute. And then we have something that is really exciting. We have also func from some input type to some output type. And this doesn't represent a value, it represents a function. And this is basically a function of some input data, x, that computes a function. And this function can be passed around like a value. And that is extremely powerful. And this is not available in any other shader graph, so I haven't seen it. Maybe it is, but I haven't found it. And then you can use those functions that you can pass around in your patch and like apply it or execute a function by providing input data for the x, and then you get some value. You will see that also. Kyle will demonstrate some applications of that. So this is very exciting, but of course it's not finished, it's only a prototype, and there are many general improvements we have to do. We don't have those nice previews yet that you see here, so this is something, of course, that needs quite some development and brain power. We don't yet have if and loop regions like we have in VL. There can be branching and looping, which is also something that is quite possible, and is also not available on different on other shader editors. And then, of course, like we want to automatically import all intrinsic shader functions that are available, like dot cross, whatever, lit, and all those functions that are defined in HLSL or GLSL. So this should work pretty automatically. So there's still a lot to do, but it's already a lot of fun, and I was very happy that Kyle joined us like 2 weeks ago. And I showed it to him, and he immediately understood what is possible, and we did some things together, and now let's have a look at them. So, I wanna...
Willst du dazu machen?
Oh, yeah, this is a bit funky, the background here. This one. Quite some stuff going on.
You can see we've made big innovations to the quad.
Root nodes. Here. So, I told you about this var of some t, right? And this var of some t represents shader code that computes a value. And in this slide here, you saw this entry point node here, this or that, and these are the things that start this shader shader code, and we already have 4 root nodes that can all be used as visual shaders. So the first one is the very simple one, but extremely powerful. It is a compute FX graph, and here you have the root, which is just any computation that you can connect anything here. build a graph, and it will run it as a compute shader, so you can read, write the buffers, textures, anything here. Then we have a standard draw FX graph, which has a vertex root. Oh yes, good point. So here you see this var of vector 4. So the vertex root shader wants to have a vertex position, which is a vector 4, so x, y, z, and w. And it has a pixel root for the pixel shader. So this is basically a very classic draw shader setup where you have a vertex shader and a pixel shader that you can fetch here. I'll show that in a minute. Then we have a texture fix. That is how we started actually. This one has an input texture that you maybe want to read. Then some texture definitions. And here's the root, which is can compute some vector 4, which is the color that will be then in the output texture. And we also have this node that you saw on the other tools, a material that takes the albedo color, glossiness, metalness, and all those values that you have, and you can also build shaders for that. So that's what we have already. And I want to quickly do a very basic draw shader that basically doesn't do much, just draws a quad on the screen. I want to show you a bit the categories in node browser and node box. So maybe the other ones. So let's just look at this one. So now we don't see anything because we don't have a geometry. Let's do quad mesh. So now this draw shader has some input geometry, which has like position, normal, things like that. And then now we can plug something into the vertex shader. And basically what we can do, the simplest thing is like just return position. And there's a node for that. But let me just have a look here in the Xenko ShaderFX category. So there's a few subcategories in the nodes. This is a bit small. So you have a few operations that we tested. You have functions, some buffer things, texture things, and then variables, which is very interesting because you can get any semantic of the shader pipeline, and you can like get members of another data type, and you have constant values like writing 2 in the shader code. It's like that. So let's take the position semantic and just return it, and that should already draw something different. Yes. So here we have the quad, and since we don't return anything for the pixel shader, it's a black thing. So let's just do an input value. So that means it's a value that goes from the CPU to the GPU and then gets written into the pixel thing. That is just called in the shader fix category. In the variables, it's just in the basics. So this one, and the cool thing is it's generic. So this one is like, can take any vector type or a float or a matrix. And as soon as you connect it, the types get inferred. So now it knows the input must be float 4 value, and now if you set this point to 1, it's that. And I think that already is quite cool because what you did here is with a few nodes, you defined the whole GPU pipeline. So you're talking with the graphics API, you're uploading the mesh to the GPU, you have this like dynamic input here. So that is basically like a huge amount of code that you would have to write if you do it in
The
C#.
implication.
Yes, I mean, that works.
It looks too simple.
It looks
Nobody believes it.
You don't believe it? Okay. So let's get.
Inside.
Yeah.
Yeah, exactly. Cache creations and loops and whatnot.
So there's also a transform in operations here. So let's transform the position. So there's no matrix input, so it disappeared. And we can, for example, also do shader. Right, and then put in, for example, transform SOT, and now we have all transformations here. So that's basically how you can fetch the shaders. And the interesting thing is here that this is not a different canvas than your other application. In here you can put things like LFOs and have a vector join, and for example animate the Y scaling or something. Right. Okay, so yeah, this looks quite boring. The technology behind is super exciting, at least for a developer. And now I want to hand over to Kyle, and he will show you some more interesting examples.
So yeah, can show you some other examples. I'll just say I've had very, very little time to play around with this, and it's quite amazing already how much you can do, how quickly. I think it's fair to say that it'll be reiterated a bit still. So what you see now isn't exactly as it'll be, but it's already quite powerful. So I'll show a couple examples. So I mean, here on the left, we're basically we just have more or less what saw already in the example. So just scaling that there. I think it's worth just noting that the way this is working, we could add other pipeline stages there as well, and it's actually really, really cool that you kind of have access to all the different shader stages. Do you guys know what I mean when I'm talking about shader stages? Traditionally, I mean, here we've got vertex and pixel shader. And when you write shaders, normally, at least traditionally, if you want to kind of pass values through the pipeline, it's quite a pain in the ass, basically. You're passing these structs kind of from one pipeline stage to the next, and if you've got 5 pipeline stages and you decide at the end that you want to add a value or remove a value, then congratulations, you get to edit all of them. And Xenko's kind of got some really cool solutions to this under the hood already, which I think are quite well kind of hooked into this system. So I mean, this position one here is a good example. I mean, he's made some like this, but we could also, I think there's a semantic node also, and what's the create one? But if you want to have a different property, or you're even using a custom semantic in your shader, you can access that as well. And at any point in the pipeline, and Xenko will kind of just take care of passing it through to the point where it's needed, which I think is really cool. So if I hook this one up to the pixel shader instead, just click that one. So we can see we've just got like a basic noise, and this is kind of funny. Like we could do this in the texture effects, but I think this is just kind of an interesting example because it's just been patched together basically in the same environment. I mean, if we want to use the set input and multiply it by like this kind of deferred function, that's fine too. So now we get colored noise. Ooh. But yeah, I think like it can't be overstated how neat it is that these are all in the same like patching environment, not just the different shader stages, but also that you're in the same environment as your application as well. So if you want to kind of be sending values back and forth, it's super easy. I think a big thing with most sort of shader graphs or most graph systems and a lot of 3D software is it's often got like a very specific domain and it's kind of walled around that that's the thing that you're doing. I think this is a little bit more unified, which is really cool. So like just as an example, I mean, these ones we've been doing so far have basically just been kind of mostly just the pixel shader. So I can switch to this one. And so here we've got a bit of noise. And again, this isn't like a specific effect that is a kind of vertex displacement effect. It's just an abstract noise function, basically. Some of these are kind of just copied out of Field Trip at the moment, but this is much more general, and like Field Trip's very hacky compared to the way this works. This is like Field Trip on steroids and everything runs native much faster. It's quite nice. So like we've got this invoke here, and basically it's kind of outputting a bar, which is in the same kind of language as the Xenko material stuff, or other types is fine as well, but it's taking the function. And what's nice about that is we can have a whole function graph that's abstract, but the context that it's in, you can change. So, you know, I mean, just as a simple example, if we wanted to run the whole function on the normals instead of the position or some arbitrary value, you can do that as well. Yeah, and then maybe like we might just see it with a bit more resolution, or we can. We were talking how it'd be cool to see something other than a sphere. So I mean here, like the pixel shader is just a constant, but you can start to see how like this is quite modular in the sense that you could have a whole sort of patched pixel shader there, and it's just starting to separate a little bit in the sense that you can patch any kind of vertex effect you like, and then mix and match how you're actually drawing it. Which is quite nice, and is kind of a traditional pain point, I think, a lot with shaders, where you have this sort of permutation explosion where you have, you know, a few different vertex shaders and you want to then shade them different ways, and it used to be you really had to write a shader for every combination. Or a lot of game studios, I think, make really crazy complicated tools to do that automatically, but it's much more kind of modular, basically. So for like a more kind of crazy pixel shader, so this one, now we've still left our kind of vertex displacement shader on, and we've got another shader running here that's actually ray marching. But you can see it's like integrating with the mesh content as well, so it correctly kind of reads and writes to the depth buffer. And you can imagine it being shaded in a beautiful way. It's just marvelous for now. So, but yeah, ray marching is good fun. It's a fun way to kind of play with these sort of composite design patterns. So we've got the sphere, we've got lots of spheres. Actually, this should still also work with the meshes. You know, I mean, you can see with the grid, I guess, that it's doing the depth. I should just say also, like, you can make the ray marching look much nicer, like if you put some FXAA on and stuff, but it's not on at the moment, but that's all good. But yeah, so we can, you know, play with how far they're spaced. Now let's add some noise to the SDF. Now they're lumpy. Maybe we don't like this color anymore, so we'll change the matcap. Let's put a plane on with it. And I mean, we're kind of building this up piece by piece, but what's really cool is it's all just abstract functions. So we could send the same function somewhere else to do something else, but also from anywhere kind of upstream or downstream in that same graph. You might use it for something else again. And then finally, let's put some 3D noise on it, which should even be animated a little bit. That one will probably give it something to think about. Yeah. Now it's wobbly. So maybe just quickly, because we weren't sure what was wrong before, we'll put the mesh back in so you can see it's in the same world. And if I take the ray marching off, you can have a very quick look at this at the material graph. So we literally like had this ready kind of as walking up the door to come here, so there's not too much can show yet. But yeah, it's basically just kind of proof of concept. So I think we've just taken like some glossiness and some metalness and attached one of these abstract noise functions to it, and there you have it, like procedural PBR. And that's quite nice because it's like, you know, at the moment it's just the position, but it can be based on anything. And it's quite nice with meshes and things, you know, even if you don't have clean UVs, procedural noise will always work. I think that's about it.
Yeah, now you've seen all the root nodes, everything basically. Yeah, that's there so far. So, do you want to see the last thing, like defining your own function in a patch, or is it already enough for everyone? Yes. Yeah. So, yeah, let's go back. It's very sphere-based, everything here. Let's go back to the ray marcher, this one, but we'll roll back all the way to the sphere, to this one. Yeah, I mean, we'll even take the non-shaded ray marcher. We have this one sphere, and now we could have a brief look at the shader code that generates this sphere, which would be here. And you can see we already have a lot of functions here. So here's the sphere SDF. It's basically, oh, it's quite small.
I think it's in the library. And if you got a definition, it will show.
But basically, you take a position, you subtract the actual sphere position from it, and then you also have a radius that you for the size. And the sphere function is pretty simple. Sphere here the happy lips, happy SDF. Here Kyle has many things up his sleeve, as you can see here. But maybe let's have a sphere. Is it?
SPH.
Oh. Here, this one. It's just the length of the position minus the radius. That's how you define a signed distance field for a sphere. And now I can show you how you can define a function that gets used by the ray tracer, so it calls like millions of times basically for each pixel multiplied by all the ray march steps. So let's have a look at this one, and it's, I think I prepared it. It's called func SDF. There it is. Let's have a look at it. It outputs this thing that you then can put into a build func node. builder here. So this one takes a node, this node, and this node defines this function, which is the same that you just saw in the shader code. Defines it. Here is the position input, then you subtract the position to position the sphere, then you take the length of it, and then you subtract the radius to have the size of the sphere. So this is basically also a bit of shader code, but it is implementing this ifunc definition interface, which tells this func builder that it can compile it to like this abstract func here that Kyle was using in the ray tracer. So now you can have a node that implements this interface, defines a function. Here you have the input arguments, which are values, but the values will be provided later by the ray tracer, ray module. So now the output here is a function which should be exactly the same as the sphere that was written in text. So let's remove this one. And if we connect this one, it should look similar. But it doesn't. Oh no, because we don't have a radius. Yeah. So we need to.
You can copy it in the sphere.
Yeah, this should be this and this should no.
Not the other way around.
Oh, was it wrong? So radius. Position is 0. So this one works. No. Okay, works on my laptop. So okay.
We see this here.
You can imagine the sphere here. Yeah. So we went from shading back to normals, back to no sphere.
It looks similar.
It looks similar. It's very similar. It looks similar to this one. Yeah, I wonder why it doesn't work. Did it change something here? I don't know.
So again, what's the purpose of that?
The purpose is that you can patch functions, that you don't need. If you're not a coder, you don't need to call your friend who is a coder to write you this kind of things. You can just patch it. That's basically the thing. And you don't have this setup that you have to define files here that then have to be in a special folder. You have to have this special syntax. You need all these references to Xenko. Now here you just define this function, you patch it, it's all in the same system, it's in real time, it gets compiled in real time. And I wonder why it doesn't work. Yeah, anyways. It is possible. Let's go back to the nice one again.
Yeah, it's usually quite quick. I can unpatch that as like see if it could break it sort of test. And
yeah, thanks for coming. Sorry for the.
Call it funky, not funk.
Funky definition. Yeah.
All right, then that's good. That was it. Questions? No questions?
Questions, ideas.
Suggestions.
What do you need to implement to have this run? So what is the part of your work now besides the patching nice noise function on patching side, but what is missing to have the bridge between Xenko and VL? You know what I mean? So what is
You mean to do?
yeah?
When can we have it?
This is the second question.
Yeah, as you can see, not all demos worked as we planned them.
Yeah.
So
That's the reason why I'm asking.
you can see if you do anything else that is not this demo, it will probably break. So this is the first thing we need to do many examples and fix all the errors that could occur, like this one. I have no idea why it wouldn't work. It was very
Is it
working very nicely.
at all worth explaining to people how you kind of have Xenko in the background here? Are they familiar with this?
Was this the question? What kind of code or what kind of work we have to do in order to?
Yeah, it's a more complex question. It's like more like what is the core you're now tackling, or are you patching a lot, or is it more like?
Yes, the cool thing is Xenko already has this idea of like this graph or this tree of shaders that you can build. I think many of you know how to write shaders. If you look at, for example, what is the simple one? Maybe the union SDF. Combine SDF. Yeah, this one. This is a very good example because what you can see here is in Xenko's shader language, which is basically based on HLSL plus some additions from them. And one of those additions is this compose keyword here. You can compose something, and the type that you compose in here is another shader. And this is basically like you, instead of setting a value as an input, you set another shader as an input. And this SDF1 here now represents this other shader that this function can call. And that is extremely powerful, and this already works super good. So basically what we have to do is like make many of those shaders that you can compose with each other, and basically avoid things like, if you have a look in this folder variable, you see there's a string variable, there's getVar, and it's implemented for each data type. There's pool, flow, flow2, things like that. And this can of course be automated, that you basically read the shader language in all the definitions of the shader language, and on demand, when the user creates a node, the type gets inferred, you just have some like string template somewhere where you just replace those types basically, instead of having a file for each type, which just will be way too many files in the future. So this is a big thing that we have to do to basically automate this process that we now have to do by hand for each data type at the shader functions. And yeah, then a big thing is also this this material node that you saw. Their materials have many more options than just color, glossiness, that, I don't know, transparency, imaging.
You can use, like, Xenko has multiple kind of PBR models already implemented and stuff, so depending what your PBR workflow is, it should be able to just work basically.
Yeah, and the other thing, instead, which is very interesting, I think, instead of having this material node with shader inputs, have this node as also a shader function definition. It can take a few inputs that are also shaders, but the output here could as well be a shader. And then you plug this shader maybe into this ray marcher, and the ray marcher provides nodes and
there's a lot of scope, I think, for like interesting and exotic data types and stuff. Like so far, I've mostly been playing with kind of standard ones. But...
Oh yes, defining your own data types is also something very important in many shaders. So that you have structs, maybe your particle, your, I don't know, light definition, things like that. So defining structures, we didn't look into that. So there are many directions we could go. And all of them are quite interesting. So therefore.
Kyle, are you hooked?
I think it's quite powerful, actually. Yeah. I don't know. I can, like, I mean, this is kind of just a prototype we're playing around with a moment, but it kind of has a fairly smart approach to it. I mean, like as you were mentioning, there's some stuff we could automate and things, but I think already as it is, it's like, from a developer point of view, much easier to add a lot of things much faster than it was kind of under the old system. Yeah, I think that's partly the system and partly also like the way I made some of my libraries. I would rethink doing that. But yeah, like it has I think a lot of potential, both from a developer point of view and a user point of view as well. Yeah. Seems cool.
Are you using this approach now to also implement things for the general Xenko implementation? For example, would you like patch the quad like this, or have you any plans of actually?
So your question is, are we using this in the Xenko library to define the basics? Yeah, I think so, because we started with very basic shaders that are quite limited. So we have a screen space one that draws just a rectangle on the screen space and can display texture. But with this, we can very quickly exchange like the world view matrix with only the view matrix or only the world matrix, and then define much quicker in which space the geometry lives and things like that. Yes, so I think very simple and basic utility shaders can be super easily made with this, which is also much quicker than writing the files, connecting the files, then on the patch within, then something is wrong, and going back and forth between shader code and patch. So yeah.
You talked about some not ready stuff like the ifs and the loops.
Yes.
And I can imagine that like if you would implement like ifs and loops, that kind of thing would integrate more. Oh, hello. Hi, Mom. How could that like then integrate more into object-oriented stuff, like building more objects that have different shader functions based on different states of the object, and that would be like even one more step, I could imagine. Are you investigating in that areas, or what's your ideas about that?
To repeat your question, so you're asking how this can be used to build more complex systems, or like integrate it into more complex or object-oriented systems.
Yeah.
And yeah, I tried to think about it, but didn't really have the time. Did you have some like ideas when you went to bed or something?
Yeah, I mean, I think there's like quite a lot of possibilities, but I mean, it's quite new that can actually play with this stuff, so I think there's a little bit of research to be done with how it can interact with other stuff. I guess, I don't know. I'm reluctant to like speak for these guys too much because I'm just kind of breezing through town and don't have like the bigger picture, I would say. But yeah, I think like that there's definitely like a lot of potential and scope for integrating with some of the other kind of VL language features for sure.
I think I remember one thing that could maybe answer your question, and it was we already have in the Xenko demos one thing that is called like a GPU particle system. that is just a node that you could place in loops, that you could place everywhere. Just has basic inputs like particle count, particle color, basic behavior inputs, which internally has a whole shader pipeline inside it. But as it's contained in a data type, you can instantiate this data type multiple times and put in different parameters into each instance of it. And you can do exactly the same thing here, because the output of it is this entity data type, which is like the common data type for the Xenko scene graph. And anything that is an entity can be plugged into the scene graph anywhere and can be instantiated as often as you want. So you can patch some basic shader things or some complex shader things, pack it into a data type, and then instantiate it multiple times and just change the interesting parameters. So, does it answer your question?
Yes, at some point. I'm thinking more about like, what if you're changing that graph dynamically? At the moment, you're kind of patching that graph, at least what you showed in the demo. But for example, a simple, like an automated switch, like switch to this function, switch to that function based on an LFO. That would be like a simple integration into a more complex system. For example, you can, the main repetition, if you don't want to have it all the time, but only if you click on the sphere, for example, then you can, at the moment, you can just, what with the standard systems you can do is that you then change some input parameters on the domain repetition, but now there is also the possibility to just disable the domain repetition, which might be even more performant than just changing the input parameters.
Yeah,
so the question is more about how quickly is the compilation of the shaders? Is it fast enough to work in real time, and can the graph be composed in objects that you're managing in your object-oriented graph?
I think if that's like something that you want to be conditioned, then for sure it's still a condition you want in the shader code. Mm-hmm. Ultimately, with these kind of compositional graph trees, it still is actually compiled in the shader when you change it.
Yeah.
But maybe something like a shader if region or something like that would be a way to really kind of integrate that logic in a way where you can have a like straight immediate response.
Yeah, I think that would be kind of a user decision or developer decision. Whether you want to actually recompile the shader, I think that's two things that you have to keep in mind. Do you want to recompile? And maybe, I think it's possible to do all that in the background, so you don't block the main move or anything. But it could have some milliseconds delay, depending on the complexity, of course, of the shader. And if there is branching or if statements or switches in the shader, then you can switch on and off. And I think, yeah, these shader compilers are also very good. So there are some predictions. So if you switch something off, it doesn't evaluate all the domains or something like that. So yeah, I think this is something that you can answer in general as a debugger.
It's not like a case of one being better than the other. It's really situational.
Yeah.
Okay. Yeah, thanks.
Are we probably close the stream? Say goodbye to people?
Bye stream. Bye mom.